Experimental tests on a portion of the turbine blade shown indicate a heat flux to the blade of 95,000 watts per meter squared. To maintain a steady state surface temperature of 800 Celsius, heat transferred to the blade is removed by circulating a coolant inside the blade. So let's look at this guy here. So that we have coolant, and this is a coolant down here. And we know this guy is circulating like inwards and outwards of the screen, right? So we're looking at it transversely. And we have the blade. The blade has a chord of length 40 mils. And the surface of this blade is at 800. And this blade is receiving energy from the air that's coming in at 1150. So because 1150 is greater than 800, we know we're going to have a Q, and our Q is going to be going from the air to the inside of the blade. And then because, let's actually redo that, as you know, it's going to be from here to here because it's warmer. And then because the blade is warmer than the coolant, then we're going to have another Q going from the blade into the coolant channel just there. 1. Determine the heat flux to the blades if the temperature is reduced to 700 by increasing the coolant flow, assuming that the local Nusselt number is unchanged associated with the change in T. And L and K are unchanged. So our length, the chord is the same in this situation, and the conductivity is the same as well. So our Nusselt is maintained, and we want to find what is the new heat flux. Okay, so question is, what would be heat flux if T blade, which we call TS, is 700 as opposed to 800? Okay, so check it out. We have, initially, we have the information for the first situation, first case scenario. We know how much energy it is absorbing if it's 800, right? So in our first scenario, Q1, we know it's absorbing 95,000, that's 95 to the third watts per meter squared for a situation in which we have a certain delta T, right? And this all comes from Newton's law of cooling that we know very well by now, which is this, and therefore Q over A, which is the same thing as little q, right, is just the convective coefficient times the difference in temperature. So if we have that heat flux and we have the delta T, then the convective heat transfer coefficient is trivial, right? So therefore H will just be my small q divided by my delta T, and in this case I just have 95 times 10 to the third divided by 1150 minus 800, which gives me 271.43 approximately watts per meter square Kelvin or Celsius. Okay, so we can find what is the convective heat transfer coefficient because we know what is the heat flux in that situation. Now, on situation 2, number 1, on situation 2, our delta T equals 1150 like before, but now our blade is 700. So that will be our difference in temperature there. Okay, and what we need to determine is what is the Q under these conditions. Well, Q is the same thing, right? It's going to be convective coefficient times delta T. Our delta T is different. What about our convective coefficient? So to be able to answer that, what is our H2, we need to look at our Nusselt number. So let's look at Nusselt on the first situation and Nusselt on the second situation because we know they are the same according to what was said. And we know the Nusselt is, the length, characteristic length times the convective coefficient divided by the conductivity, right? We know that from our last class. So that means that I can make this like so. Length of the first one times the convective coefficient of the first one divided by conductivity of the first one, length of the second one, convective coefficient of the second one, conductivity of the second one. Now, interestingly enough, the L and K are unchanged. Okay, so if they're unchanged, that means that L1 equals L2, K1 equals K2, and if that's the case, then what happens? Well, this just says that H1 equals H2. And if H1 equals H2, then how easy is that for us, right? Because we can go back into this equation over here, and we can solve what we're looking for. My Q2 equals 271.43 times 1150 minus 700. And then I would expect this to be greater than my Q1 because I have a greater difference in temperature. And indeed, we get 122.1, is it? 0.1 thousand watts per meter squared. So this would be the answer to the first part of the problem. As for the second part, let's read the second part. Determine the heat flux at the same dimensionless location for a similar turbine blade. Okay, watch out for this. Having a chord length of 80, so we're increasing the chord length. Now we have a blade that's bigger, that's 80 now. When the blade operates in an airflow at 1150 Celsius, velocity of 80 meters per second, and surface temperature of 800, assuming that the local Nusselt number is unchanged. Okay, so once again, our local Nusselt number is unchanged. We can once again derive some insights from that. Situation 3 now. And we want to know what is Q3 for delta T of 1150 to 800. Okay, so first thing to know is that if my convective coefficient is the same, then Q3 would be the same thing as Q1, right? But we need to check if that's true, because now we have things that did change. So what did they say? They told us that Nusselt on situation 1 equals the Nusselt on situation 3. Okay, or if you will, situation 2, because they're all the same, right? Now we can once again write this in a different way. We can write that convective coefficient 1, length 1 divided by K1 equals H2 L2, oh, not 2, 3. 3K3. Right, now there's a very important sentence, which is the one that I highlighted, which says that the two blades are similar turbine blades. So what can we eliminate from this equation here? That will be the same.
Okay.
Right on. Right, so similar, so because they're similar, my K3 and my K1 will be approximately equal. And if they're approximately equal, then this means that my H1 times my L1 equals my H2 times my L2, which means that my H2, sorry, not 2, 3, right? Which means that my H3 equals my H1 times L1 divided by L3. Okay, if you guys remember, this fellow here is 40 mils. This fellow here is 80 mils. So it's literally just half, right? So it's half of H1. So it's just H1 over 2. But let's leave like the whole thing for now, and let's try to write our equation down. So what is the energy on Q3? That will be H3 times delta T for the third scenario. And this is just H3 times 1150 minus 800. And then our H3 is just H1 of L1 over L2, 1150 minus 800. If you guys recall, this times this, we know what that is already, right? That will be Q1. That's what we had in the first situation, right? So this is the same thing as saying Q1 divided by 2. Okay, so you can just take Q1 divided by 2. But let's not do that. Let's be very conservative and actually solve for the whole thing. Let's put down the numbers and see this happening in front of our eyes. So our H1 would be 271.43. Our delta T, 1150 minus 800. And our L, let's actually put them down. So that will be 40 mils. I can convert that into meters if I want to be very conservative, even though they're going to go away as soon as I divide them. And if we plug these guys in, you're going to see you're going to get 47.5 thousand, which surely enough is half of Q1. So this is answer for our second part of the problem. Okay, so it's once you have the convective coefficient, things are so much easier. Now we're talking about a blade here, turbine blade, and I know that can be a bit distant for some of you guys, but we can also relate this back to a computer, if you will. Okay, so if you picture a heatsink on a computer, and we know some high performance computers actually use coolant, right? Use coolants, water coolants or things like that to cool down the things. Let's think of I'm going to draw a little processor over here, and this guy is heating up. So T over here is going up, and therefore we don't want that T to go up, so we don't want it to malfunction, right? So we can have a coolant down here that's going through this guy, and it's taking away some of that energy. And the way this coolant works, the same process, right? Because this T is greater than the treated coolant, we're going to have Q going from the processor into our coolant, and the situation is analogous to the one we just saw on the blade, right? We're going to have a certain coefficient. We can calculate that coefficient. We can find how much energy it's taking away. So it'll be analogous to the thing we just saw on a different example from something that might be more relatable to your everyday lives. Questions?